Hi, my name is Tony Yates, and I'm a home brewer. And like so many others, I got started with just buying a kit in a store and a bucket. From the time I started until my all-grain system was done, I had made what I thought was pretty good beer. You know, it's like many other people, you share it with your family, you share it with your friends, and everyone pretty much agrees that, yeah, your beer's okay. But almost everyone would say, okay, that tastes like homebrew. And really, as a home brewer, you're kind of striving to make beer that tastes great. Not necessarily like some of the mediocre stuff you buy in the store, but you want to be able to make great beer. Over the course of the last 5 years, I've learned a lot about the different influence that water can have on your beer. And in this video series, I'd like to go ahead and share with you some of that knowledge and share a little bit of my experience in terms of how to improve your water for the specific style of beer that you're going to brew. I can't count the number of times that I've heard somebody say, I've got great water, I can brew really good beer. Yep. That's a funny thing to hear because I know that not every water source is good for every style of beer. Generally, the water that's coming out of your tap has some sort of contaminants that need to be removed, but above and beyond that, that water is probably a profile that targets one style of beer. How often have you brewed one style of beer and had it turn out great, only to brew another style of beer and it turns out sort of mediocre? And what you kind of find over time is that you can brew one style of beer really well, but all of the other different type of styles that you're trying to brew, not so great. So what I'd like to share with you is basically how you can tune that in and really understand why you can brew one style of beer great, and how you can adjust your water so that you can brew all different styles of beer great. And water can be confusing because you'll often hear a lot of different terms that are related but mean different things. Things such as alkalinity, total alkalinity, residual alkalinity. All of these things play a very important role in your brewing water. And I want to go ahead and talk about these things and explain them in such a way that is easy to understand. I want to talk about hard water, soft water, alkaline water, and the things that you can do in order to treat the water to be better for a specific style of beer. So where do we begin? I kind of like a bottom-up approach and start at the very bottom and sort of work our way up. And starting at the very bottom means talking about things that might not necessarily seem relevant, but they are in so many different ways. In this video, I specifically want to talk about atoms and ions and how they interact with each other so that you can see the types of changes that are going inside your brewing water on brew day. This matters to both all-grain brewers and extract brewers equally. So during this talk, I'm going to be talking about pH, and that affects extract brewers just as much as it does all-grain brewers. pH is extremely important. So if you ever want your neighbors to be able to ask you, is this an all-grain? Or is this an extract? Is this a homebrew? Or is this store-bought? You know, that's going to be a compliment to you, and it's going to be basically all reliant on your water. So come with me into this story of water. Hopefully I'll be able to shed some light onto the details, make things clearer, and explain them in such a way that's easy to understand and gives you practical ways to apply these things to your brew day. Let's get started. To kick things off, I'm going to start to discuss the basics of atoms and ions, as well as talk about how they play an important role in determining your water pH. Now, first and foremost, I'm just an average home brewer. You know, I've got a curious soul that likes to learn the details of whatever it is I'm involved in, and these days, that's mostly home brewing. I'm not a chemist, I'm not a water expert, I'm simply going to share with you what I've learned by reading great books like Brew and Lager Beer by Greg Noonan, as well as Water, a comprehensive guide for brewers by John Palmer and Colin Kaminsky, as well as digging into materials that were provided by A.J. DeLange, which I believe was a pretty big influence on the water book. Well, I've chosen to start off at the beginning. a bottom to top approach, if you will. I want to start off by talking about atoms and ions and the interactions that they have with each other and its effects on your pH and alkalinity. I mean, these might be hard topics to talk about, but hopefully I'm going to be able to abstract them in such a way that makes them easier to understand. So, without further ado, there are several types of elements that have been discovered, right? And in regards to brewing water, we're only interested in a handful of these. Primarily hydrogen, calcium, magnesium, sodium, carbon, oxygen, sulfur, chlorine, and also phosphorus too. Well, I'm not going to go into detail about each one. I will mention that hydrogen is the key in determining pH. There's a small concentration of hydrogen in your water on a fractional level that determines whether or not your water is acidic or alkaline. And I want to go ahead and talk about these things and why those things are important. So all atoms are different, right? Their appearance, their weight, and effects on the world. Yet they all have basically the same purpose, to bring existence to reality, and beer is such a lovely thing to have in existence. All atoms are made up of equal number of positive and negative charges called protons and electrons. And in fact, that's the property that determines the chemical element in the periodic table, is the number of protons and electrons that each atom has. Because atoms have an equal number of positive and negative charges, protons and electrons, that means that they don't have a positive or negative charge. They're neutral. Here we see hydrogen, oxygen, and magnesium. Hydrogen has 1 proton and 1 electron. Oxygen has 8 protons and 8 electrons. Magnesium has 12 protons, and you guessed it, 12 electrons. So you might also remember that on the periodic table, hydrogen is element number 1. Oxygen is element number 8, and magnesium is element number 12. And the reason why is because these are the number of protons and electrons that they have. That determines their weight, which determines where they appear on the periodic table. There are a couple different types of atoms. We have stable atoms and we also have unstable atoms. The difference is that the stable atoms have 2 electrons on their innermost orbit and 8 electrons on their outermost orbit. So knowing that, you can see that none of these atoms here are considered stable atoms. Let's go ahead and take a look at a stable atom. The neon element has 2 electrons on its first orbit and 8 electrons on its outermost orbit, and therefore it's stable. It can retain its form for eternity. Unstable atoms, however, will decay. It's entirely possible for elements to have more than 2 orbits. I mean, they can have 2 or 3 or 4 different orbits of electrons. So it's totally possible for an atom to have a third outer orbit with only 1 electron, and in that case, it's considered an unstable atom. I refer to these as orbits, but the circles are actually called valence shells. The good news is that unstable atoms is that they can give or receive electrons to and from one another in order to form an ion that has a stable electron configuration. So what is an ion? An ion is nothing more than atoms that have given or received electrons from one another. So not everything is all hunky-dory forever though. Here you're looking at pure water molecule, where there's 2 hydrogen atoms that have shared their electrons. This is water in its purest form. But how often do you find pure water source? Never. Nearly all water on Earth is some diluted solution of gases and organic matter. Even our rainwater contains any number of elements, and bicarbonate is even in our rainwater. And unless you have well water, your tap water source is likely to be treated with some form of chlorine or chloramine to inhibit microbial contamination. So that in and of itself is like the first thing you need to learn how to do. We need to get rid of the chlorine or chloramine in your water. If you don't, you could have the best brew combination of grains and hops that you want. You add in that yeast, it's going to make beer, and more often than not, 95% of the time, you're going to have an off flavor. And that off flavor is a direct result of the chlorine that was left in the water. And the most popular off flavor that you will get is a medicinal flavor. It's called a phenol. It could taste like a Band-Aid or some sort of solvent compound in your beer. Nobody wants that. So do your best to get rid of the chlorine or chloramine, and there are several different ways to do this. I'll go ahead and put some links down in the description of this video that will explain to you in detail how to get rid of chlorine and chloramine in your water. An alternative to that is just to use reverse osmosis or deionized water. Either one of those are great Brewing water sources. So if you have access to those things and they're, rather inexpensive, then go ahead and start off with that type of water, because it's pretty much, you can build any water profile to target any beer style with those the easiest. So as seen in the previous slide, atoms become ions by sharing electrons. They come into close proximity with each other, and all of a sudden they become promiscuous. They transfer one or more of their electrons to become an ion. Take sodium and chlorine, for example. Sodium lends an electron to the chlorine element, and together they form sodium chloride. Now that the chloride side of the ion has one more electron than it has a proton, this causes an imbalance, and therefore it's no longer a neutral charge. Because it contains more negatively charged electrons, it has a negative electromagnetic charge. In this case, the chloride ion is referred to as having a negative valence. The sodium ion, now containing more protons than electrons, positively charged, and referred to as having a positive valence. Ions that have a positive attraction are called cations. Negatively charged ions are called anions. The easiest way to remember what a cation is and what an anion is that cats are sort of positive creatures, right? Not all, but most. And it certainly are the pictures of cats on YouTube. But anions, you can think of these as like a negative ion. Anion, a negative ion. Okay, so cations and anions combine with other elements in order to form ionic compounds. Here you can see the most common Brewing ions: calcium, magnesium, sodium, bicarbonate, sulfate, and chloride. Cations are positively charged because they have more protons than electrons, and therefore they contribute more towards the acidity of a solution. Anions are negatively charged because they have more electrons than protons, and therefore they contribute more towards the alkaline aspect of a solution. When you get a water report, these are the ions that you're more interested in knowing. So they have the strongest influence on predicting your mash pH, which is different than your water pH. Now, a water report is pretty important. I'm not going to lie to you. Talking about water and not having a water report is a little bit horse without the carriage, should I say. You need to have a water report. The best case scenario you can expect to have is to get a water report that tells you what the calcium is, what the magnesium is, what the sodium is, what the sulfate is, etc. But you can get away with understanding just two pieces of information: what's your total hardness and what's your total alkalinity. Using that information, we can also make some pretty good guesses about what you're going to need to do in your water in order to target different styles of beer. Okay, now that the water report information is out of the way, let's go ahead and start focusing in on pH. What is it? I said that hydrogen pretty much plays the host of the party, and it really is. So what is its particular role when it comes in determining pH? Well, when there are millions of atoms and ions and molecules in a solution, there's this thing called disruption. It's also referred to as dissociation. It's a constant state of flux in your water, even in pure water. Because there's an overwhelming number of H2O molecules in solution, a small number of water molecules will spontaneously dissociate. The concentration of hydronium ions and hydroxide ions are mutually tied to one another, so that when the concentration of hydronium ions goes up, the concentration of hydroxide ions goes down. When the concentration of hydroxide goes up, the concentration of hydronium goes down, which basically means that when your pH is lowered, it's increasing the number of hydronium ions, and it's decreased in the number of hydroxide ions. When your water pH increases, then the concentration of hydroxide ions is increasing, and the concentration of your hydronium ions is decreasing. A bare hydrogen ion has no chance of surviving in water. The protons with a strong positive charge is attracted to any part of a nearby atom or molecule that has a negative charge. The hydrogen ion that has been donated their electron to another oxygen molecule almost immediately combines with another water molecule in order to form a hydronium ion. In water, the concentration of these ions is a constant called Kw, or constant water. It's temperature dependent and has a value at room temperature between 10 to the 14th. This equation tells us that anything that raises the concentration of hydronium must also lower the concentration of hydroxide, basically to keep the value of Kw constant. So water with an equal concentration of hydronium and hydroxide is considered to be exactly neutral. That's a pH of 7. Water with more hydronium must have less hydroxide, and such water is acidic. So water with less hydronium and more hydroxide is going to be basic or alkaline. When it comes to reading the pH values, I think it's pretty important to understand that 6 is more acidic than 7. It's 10 times more acidic than 7. And that 5 is 100 times more acidic than 7. There's sometimes confusion between pH and alkalinity. So while pH and alkalinity are related, they are different in that pH is a measure of how acidic or basic a solution is. Alkalinity protects pH against rapid change. Alkalinity is the buffer that determines how easy or difficult it is for the pH of a solution to change. You'll also hear people refer to this as the buffering capacity of water. That's alkalinity. It prevents the pH from changing. Alkalinity is the measure of how much acid neutralizing compounds are in a solution. And when I say acid neutralizing, I'm talking about things like bicarbonate, carbonate, and hydroxide ions. So here's an example of the carbonate species. I think it's important to understand that the different carbonate species have different forms at different pH levels. For example, while chalk easily precipitates out of solution when the pH is less than 8, it's more likely to stay in solution when the pH is higher than 8. I want to get more into the carbonate species and how they affect mash and a beer pH, but I'm going to do that in a later video. Let me just summarize by pointing out the difference between pH and alkalinity. pH is the measure of acid or basic in a solution. It's the degree of how much hydronium exists in that water. Alkalinity is the buffer that protects against sudden change in the pH of water. It's how much buffering capacity or acid neutralizing compounds are in that water. And how much is in there will determine how hard it will be to change the pH of that water. So let's go ahead and talk about measuring pH for a minute, because this is something pretty important that I think a lot of people sort of screw up. I know I have. When it comes to measuring pH, the minimum thing that you need is pH strips. But I don't recommend that you use them because they're almost guaranteed to be off. The color is going to be a little bit different. It's going to be hard to read and things like that. The only true way for you to understand what your pH is to get an electronic pH meter. Not an analog one, you want a digital one. I've had 2 in my long 5-year brewing career. I've ruined this one. This one, served me really well for about a better part of a year, but at the time I didn't really know how to use it that well. I would stick this in the mash at like 65, 66 degrees Celsius, take a reading, be okay with it, write that reading down on my brew sheet, and be done with it. I tell you, that's the fastest way to kill a pH meter. And when you spend $100 for one of these things, that's a waste of $100 just by sticking it in your mash water. Don't do that. When you read pH meter, you always want to take a sample, cool it down to room temperature. That's like the most important thing. All pH readings are measured at room temperature. The only time that you're ever going to see a pH reading that is different than room temperature is when somebody explicitly says it's something different. Otherwise, it's always room temperature. When you see John Palmer or anybody talking about taking a pH reading and that your mash pH should be between 5.2 and 5.6, depending on the beer style, they're talking at room temperature. It's the same thing when you take a wort sample and you want to figure out what your gravity is. You take that sample, you cool it down to room temperature or whatever temperature that your hydrometer is calibrated for, and then you take that reading. Yes, there are calculators that can tell you what the different reading is going to be based on the temperature change, but I tell you what, if you want to be absolutely positively sure, cool it down to the temperature that your hydrometer is rated for, and you're guaranteed that that's going to be the correct gravity reading. Same thing applies to pH. Cool it down first between 20 and 25 degrees Celsius, and you'll be fine. If you end up sticking one of these things in your mash, and it ends up dying prematurely, it's your own fault. If you want to be a cowboy and you do take a pH reading at those mash temperatures, understand that the pH is between 2 and 3.5 degrees lower when it's measured at those higher temperatures. So you're going to want to adjust for that. To summarize, atoms start out electronically neutral. Same number of protons and electrons. Ions are nothing more than atoms that have gained or lost one or more of their electrons. pH is a figure that expresses the acidity or alkaline nature of a water solution. Acid is the result of more hydronium ions in a solution. Basic alkaline is the result of more hydroxide ions in your solution. And pH is always measured at room temperature. Alright, so that's basically all I want to talk about for this video. In the next videos, we'll talk more about alkalinity, also about hardness, and get into those details. In future videos, we'll talk about the differences between alkalinity, total alkalinity, and really hone in on residual alkalinity and how you can use that to predict what your match pH is going to be based on your grains. So I hope that you enjoyed this video and learned something about ions, water pH, and alkalinity. If you like this video, please go ahead and comment down below. Let me know how this topic sort of resonates with you. Appreciate it. Thanks for watching.